Your phone never finds the right answer. Not once. When it tells you you'll arrive in 8 minutes, it isn't reading that off a chart, it's guessing, correcting, guessing again, throwing out a stream of numbers that creep toward the truth and never quite land on it. Your calculator does the same thing when you ask it for the square root of 2. So does an AI while it's training. None of them ever touch the true answer, they can't. They stop the moment they almost stop moving. That rule, never arrive, but settle in exactly the right place, was written 200 years ago by a man crawling out of a revolution, handed one nearly impossible order: take the most powerful tool in science, and make it honest. He almost pulled it off. And the whole thing balanced on a hole he never saw. One question runs through everything today: how can a number you never touch be pinned down? Start with the simplest picture there is. 9/10. 99 hundredths. 999 thousandths. Keep going. This little parade of numbers is sprinting at one, crowding closer and closer, and yet not a single number in it ever is one. So does it actually get there, or not? Hold that question. Everything Cauchy built is an answer to it. Here's the mess he walked into. For 100 years, calculus had worked beautifully, and it was built on something called the infinitely small, a quantity that behaved like 0 when that was convenient, and not 0 when that was convenient. A bishop named Berkeley mocked these things in 1734 as the ghosts of departed quantities. He was right. Nobody cared, because the math kept giving correct answers: planet orbits, cannon trajectories, the load on a bridge. Then the French Revolution tore the country down, and the new France needed engineers, fast. The heart of that effort was a school in Paris, and in 1816 its calculus chair went to a stubborn, devout, royalist 27-year-old named Augustin-Louis Cauchy. He refused to teach it just works. He decided to hunt the ghost down. His whole rebuild came down to swapping one idea for another. The old way leaned on that fuzzy, unspeakable infinitely small. Cauchy threw it out and said, let's only talk about something anyone can check. I can make the gap as small as you want. Picture it as a game. You play the skeptic. You say, can you get within 1,000th of one? Sure, from the third number on, we're inside. Within a 10 millionth? Sure, a few terms later, inside, and we stay inside. Whatever gap you name, I have a from here on. Win that for every gap you can name, and we say the limit is 1 even though the parade never lands on 1. Let's give the two players names, so we can call on them later. The gap you pick, mathematicians call epsilon. Just think, the small number you chose. The place where I say from here on, they call n a position, the nth term. Then the whole definition is one sentence: no matter how small your epsilon, I can find a position n so that from the nth number onward, every number sits within epsilon of the target. Take 1 over n, heading for 0. Pick any epsilon, I just take n to be 1 over epsilon, round it up. Past that point, 1 over n is smaller than your gap. Every time. But not every parade has a destination. Take 1, minus 1, 1, minus 1, forever. Does it have a limit? No, and here's the proof, not just a shrug. Suppose it did, call it L. I pick the gap 1/2. From some point on, every term should sit within 1/2 of L. But the terms keep flipping between +1 and -1. For +1 to stay within 1/2 of L, L has to live between 1/2 and 1 1/2. For -1 to stay within 1/2, L has to live between -1 1/2 and -1/2. Those two homes don't overlap. No single L can do it. So there's no limit. That's why asking is there such an n is a real test. It cleanly tells convergence from chaos. Cauchy turned the same key one more time, to define continuity. We all feel what continuous means: a curve you can draw without lifting the pen. But without lifting the pen is too vague to build on. So he made it a game too. A curve is continuous at a point C if, keep the input close enough to C, and the output stays as close to the value at C as you want. You name how close the output has to be, I answer with how close the input has to be. Same handshake, one floor down. And you can see exactly where it fails. Watch a function that jumps. Just left of the jump it sits low, at the point, it leaps up. No matter how close your input creeps to that point from the left, the output is still a whole step away. It can never squeeze into the band you asked for. So that point is broken, not continuous. One quiet warning for later: in setting all this up, Cauchy blurred two ideas that aren't the same, being continuous point by point, and being continuous evenly across the whole line. That little blur is going to grow into a theorem that stays wrong for 30 years. Now the move I think is the cleverest of all. To use the limit is L, you have to know L. But most of the time you don't. Not knowing is exactly why you're computing. So Cauchy stopped staring at the target and started watching the sequence itself. If the terms get within any gap of each other, if, past some point, any two of them are basically on top of each other, then the thing has settled, whether or not you know where. He called it a Cauchy sequence. And this is not a museum piece. This is the stop button inside every algorithm you use. Your calculator finding a square root, Newton's method, an AI grinding down its loss, a GPS refining your position, a solver chewing on equations, none of them can compare against the true answer, because they don't have it. They watch whether the numbers have stopped moving relative to each other. When you click done, you're using Cauchy's idea from 1821. Here's where it turns. Cauchy was so close. He even wrote down what looks like a perfect test: a sequence converges exactly when it's a Cauchy sequence, bunch up, and you're guaranteed a home. One direction of that is free and always true: if you arrive somewhere, of course you bunch up. But the other direction, bunch up, therefore there's a number waiting to catch you, that one is not free. It demands that the number line have no gaps. That property has a name: completeness. Watch it break. 1, 1.4, 1.41, 1.414, the decimals of the square root of 2. Every one of them is a fraction. They bunch up perfectly, a flawless Cauchy sequence. But what are they racing toward? The square root of 2, which is not a fraction at all. Quick proof: if it were a fraction in lowest terms, squaring gives p squared equals 2q squared, which forces p even, and then q even, but they were supposed to share no factors. Contradiction. So on a number line made only of fractions, these numbers sprint at a spot where nothing lives, a hole. The bunching up test fails. Cauchy's entire rebuild silently assumed the real line is solid, complete, hole-free. But in 1821, nobody had actually constructed the real numbers. He stood on a floor no one had ever inspected. So here's what he left us. 3 pieces. The limit: get as close as you want. Continuity: inputs close means outputs close. And the Cauchy sequence: judge it by how tightly the terms cluster, the stop button under every calculation. And underneath all three, one premise he never proved: the line has no holes. He nearly made calculus honest, on a number line that didn't exist yet. You don't have to arrive to have a destination, you just have to be unable to stay away. Two things are still waiting: a mistake of his that will stand, looking correct, for 30 years, and that hole, which won't get filled for another 50. Next time, the theorem that was wrong for 30 years.